Question number 1. Methane gas reacts with oxygen gas to produce carbon dioxide and water vapor. So this is a typical example of a combustion reaction. So from experience, we know that combustion reactions, they produce a lot of heat, they're spontaneous, and if you look at this equation, you can see that the number of moles of gas, so here's 1, 2, so 3 moles of gas for the reactants, 3 moles of gas for the products. The delta N, the change in the moles of both the gas and the system, because here in the system everything is a gas, it's 0. There's no change, right? 3 to 3 becomes 3. And so this means that, especially because they're all of the entire system is just composed of gas, there's no change in the number of moles, then the entropy change is going to be very small. So let's start by calculating the enthalpy of the reaction. So we do this by looking at the table that Dr. Lottie provided on the worksheet to look up. You can look it at in the appendix of your workbook. But the enthalpies are calculated by the heats of formation. So if you look on the table, if you look for carbon dioxide, you'll see that there's going to be like the entropy, then the enthalpies, there's going to be a lot of different values. So look at the value for enthalpies, the heat of formation. So for carbon dioxide, it's going to be minus 393.51. Okay, for water, it's going to be negative 241.82. Okay, so for water, be careful. There's going to be one value for the liquid. There's going to be a value for the gas. Make sure that, see, in this equation we have gas. Make sure to use the one for the gas. Okay, that's a common mistake people make. And then for for methane, CH4, it's going to be minus 74. So here you can see that for the products, when calculating the enthalpy for the reaction, the products have positive coefficients. So carbon dioxide has +1, water has +2. For the reactants, we have negative coefficients. So here we have -1, right, for methane. If you look on the table for oxygen gas, the heat of formation is 0. This is because oxygen exists in its natural state, it exists as oxygen gas. So like nitrogen gas also will have a 0 heat of formation. This is just what we call the standard state, the reference state. So elements that exist in their natural state, they have 0 heats of formation. So therefore, this is going to be around negative 802.34 kilojoules. Okay, so we can also calculate the bond energies, the change in the bond energy. So this, you have to look at the bond energy table. So bond energies are calculated by the bonds broken minus the sum of the bonds formed. Okay, so here we see that the bonds broken are going to be, we're going to break 4 CH bonds. So let's see, the CH bond is about 412. Okay, we're going to break 2 oxygen double bonds. So that's going to be 495. Okay, now we're going to be forming 2 C double bonded to an O, 799. And then we're going to be forming 4 OH bonds. Okay, because in water there's 2, right? But we have 2 water molecules, so that's going to be a total of 4. And this will give us a total of about negative 812. Okay, this is also going to be in kilojoules. Okay, so let's go to the next part of the problem. So, as we said earlier, the delta N for the gas is 0. So there's going to be no work done. So delta N for the gas, right? 3 moles of gas becomes 3 moles of gas. 3 minus 3 is 0. No change. The delta N for the system is also 0, right? because the entire system is made of gas. So again, it's just 3 moles of gas minus 3 moles of gas, 0. Okay, now let's calculate the delta S, the entropy. So again, looking at the table now, instead of looking at the enthalpies, you want to look at the entropy values. So again, this is going to it's the exact same type of calculation. So with carbon dioxide, we're going to have in the products, we're going to have positive coefficients. So 213.74 for carbon dioxide plus 2 times 188.83. Again, make sure that you're looking at the water vapor, not the liquid water. Okay, and then now we're going to subtract 186.26 for methane. Okay, and then we're going to do 2 times 205.14. This is for oxygen, okay? So this is going to be about -5. Okay, this is going to be in joules and then per Kelvin. Okay, but if we want to calculate T delta S, that means we're going to do, so we're going to, instead of using 298, we're going to round to 300. So we're going to do 300 kelvins times this number. This is going to be about -1,500, right? And the joules, and this is going to be -1.5 kilojoules. Okay, and so now that allows us to calculate the delta G using this equation. So this is what we calculated earlier, right? This is also what we calculated. So remember, we want to keep these all in kilojoules, right? That's what we convert them all to. Okay, and so this is going to equal about -800. So if you look here, the entropy change is actually very small. So it's exactly like how we predicted. Okay, and here the delta G is negative. So that means it's spontaneous, right? So we predicted that from experience, we know that combustion reactions are spontaneous. So the calculations agree with our predictions.